Okie dokie, here I am to do a hopefully short review for the test over probability and confidence intervals, and I'm just going to say that I would expect there to be a lot of probability computation questions and being able to do the tree diagrams and stuff like that, so make sure you're familiar with that. Not a ton of calculating for the most recent information because of course we just learned that, but it's still fair game for the exam, especially those conceptual questions, so make sure you're able to do that for this test. Alright, I've uploaded two things into D2L for you to take a look at. They're sample questions for exam 3. One looks like this, and it's about allergies and placebos and stuff like that. And I mentioned, I did, when I was doing scatter plots and line of best fit a couple of videos ago, I used some of these as my pictures. I just kind of used them so that I could cheat a little bit. So make sure that you can do those. I would point out that on both of these files that I've uploaded, there's a key at the back that tells you what the answers are supposed to be. So don't look at that and then put the answer. Make sure you work them first and you think you are convinced of your answer, and then go ahead and check. Okay, so use that to check your work, not to necessarily use it as your prop. Don't use it as a prop. Okay, so here we go. I'm just going to work a couple of these and then I'll scoot to the other page because I think that there's just these first couple are the ones I want to look at, and then because I didn't talk about them the other day, and then the probability questions I think is where I'm going to focus this. If we were in a face-to-face class, I would ask for questions about stuff you don't remember or still don't quite understand, but I'm going to have to wing it and hope I hit some of the stuff that you're questioning. Okay, so number one here. What's the probability that a randomly selected person either was given the placebo or improved? So this is one of those, you're given this table here, and this is one of those where there are overlaps. So if you're not sure, go back and watch videos about different kinds of probability. This is a situation where there can be an overlap. So in other words, in this particular table, this is people who got the allergy drug on this column, people who got the placebo in this column. These were control, so no treatment, that kind of thing. Total here. All right. So here on this row, these represent people who have showed improvement. These represent people who did not show improvement, and this is the total. Just to make sure that everything lines up, right? There should be 500 total going this way and 500 total going this way. Okay, so be careful because this is an overlap. So it's an or statement. And if you'll remember, or means what? Or means add, Dr. Webster. That's what I hear in my head. Okay, so it means add because it's an overlap. So basically we're going to do the probability of A plus the probability of B. That's the add part because of the or. But because it's an overlap, we have to worry about double counting. Okay. We have to worry about those people who are in both groups. We don't want to count them twice, okay? So we're going to do probability of A plus probability of B because it's an or statement, it's add. But then we always subtract out the probability of their intersection, right? Okay? Or if you're really on top of it, you can make sure that you don't count them to begin with. But I'm going to do, this is the formula that we use, right? And so that's the way I'm going to do it to make sure we're okay. So this said, what's the probability a randomly selected person either was given the placebo? Okay, so that's this column right here. Everybody see that? Given the placebo. Or they improved. Okay, so that's this row right here. And if you're not sure, those overlapping people are people who both got the placebo and they improved. So that's the N, that's the intersection. So I'm going to stay right here. This is my intersection. So I can count them once, okay? They get to be counted, they get to vote or whatever, they get to go to the party, but they do not get to be counted twice. So I need to make sure that if I add them straight on, probability of A plus probability of B, I need to make sure to come back and subtract those that are in the intersection. So let's be careful about this one because I need to make sure I've got those probabilities going right. So what is if the probability of A is the probability that these people got the placebo, that's my first event, right? Be careful because the probability is not 85, okay? Remember, all of your probabilities are between 0 and 1. So it's not 85, it's what? 85 out of how many total outcomes do I have? 500, right? So it's 85 out of 500. Okay? So 85 of the 500 people got the placebo and were in the improvement. Oh, I'm sorry. That's the intersection. Never mind, don't listen to Dr. Webster. That's the intersection. I'm going to talk about that in a minute. How many people got the placebo? That's this whole entire column, right? Ah, man. It's even worse. It's 200. So it's certainly not 200. That's not my probability. It's what? 200 out of 500. There we go. Sorry about that. Let's focus in on that intersection. All right. So what's the probability of B if we're talking about the probability of showing improvement? Okay. So probability of improvement was this one. That's 271 people showed improvement. So is it 271? No, Dr. Webster. No, it's 271 out of 500, right? Remember, whenever you do this math, this should be somewhere between 0 and 1, and this should be somewhere between 0 and 1, okay? So the probability of A intersect B is the probability of they took the placebo and they improved. Okay, so remember that's your intersection. So this is the 85. 85 out of 500 people are in that intersection. Okay, so once you've identified your different subgroups, your different probabilities, then we can do this. Probability of A plus probability of B minus the probability of A intersection B. So, and this is where it comes in handy if you left them all with the same denominator, right? I've mentioned that a couple of times, I think. So this will help out. So it's 200 over 500 plus 271 over 500 minus, take out, don't double count that intersection. So they only get one vote, not two. Minus the 85 over the 500. And remember, when the denominators are all the same, we can just kind of ignore the denominator, just put it down there, and just add 200 plus 271 minus 85. Add the numerators. So that is 386. Okay. Now, that's my actual answer. If you look right here, this was a multiple choice question, and they don't have 386 over 500. So what does that tell me? You need to go ahead and divide it out, right? 386 divided by 500, if you do that arithmetic, is 0.772. Okay, and that is how they got that the answer is D. Okay. All right. This one is talking about correlation, so make sure you can go back and look at that. State whether you believe the two variables are correlated. Okay, if you believe they are correlated, state whether the correlation is positive or negative. Okay, the weight of a textbook and how well it is written. Okay, so this might mean, so what is the possibility? The heavier the textbook, the better the writing? Thumbs up, thumbs up. The lighter the textbook, the lighter the writing. Thumbs down, thumbs down. Those are both positives, right? Or, so that would be a positive correlation. What do we think about that? I don't think so, right? Just because the textbook is really big and thick doesn't mean it's well written. Okay. Or the heavier the textbook, the worse the writing. Some people might actually think that because they might think, oh, I don't want to read that because it's so heavy. But that's probably not true either, right? I would bet that the weight of a textbook really doesn't have much to do with how well it's written. How well it's written may be dealt with by the experience level of the author and stuff like that. So in that case, I don't think these have anything to do with each other. Not correlated. Now, if the question was something like the weight of the textbook and how much back strain you have when you're going to class, yeah, that might be a positive correlation, right? The heavier the book, the more your back hurts. But that's not what it said. All right. So, again, there's those scatter diagrams there, and you're supposed to be estimating the correlation coefficient. So work through some of those, make sure you understand the answers, and so on and so forth. All right. So I'm going to look at the other one real fast. Okay. And I would say if you're not sure about some of these, just go back and look at the videos again. Watch them again. Do some of the homework. Number 1 on this one, I'm just going to work a few at random and then I'll move on. Number 1 says on a multiple choice test, each question has 4 possible answers. Okay, stop. If there's only one correct answer, what's your probability of getting a correct answer if you just guess? There's one possibility, one correct answer, but there's 4 choices. So it's a 1 in 4 chance of just randomly guessing, right? Okay. It says if you make a random guess on the first question, what's the probability that you are correct? 1 in 4. Okay. What if there were 2 questions? And you guessed on both of them. So what's the probability you'll get the first one correct? 1 in 4. And what's the probability you'll get the second one correct? 1 in 4. And remind me whenever I say and like that, and means multiply, right? Okay. So what's the probability that you'll guess on 2 multiple choice questions on this test when it's a 1 in 4 chance, 4 possible answers per, and get them both correct? Well, it's only a 1 in 16 chance that you'll get both of them correct, right? So watch out. Person randomly selected, find the probability that his or her birthday is in December, ignore leap years. Okay, the answer was 31 because there's 31 days in December out of 365. So remember that's like a relative frequency. Okay, probability, it is not a theoretical probability. So we have to go through and look at how many days are there in that particular month and relate that back to the total days in the year. The class consists of 60 women and 80 men. If a student is randomly selected, what's the probability the student is a woman? Well, it would be what? 60 women divided by the total, which is 140. And then apparently when you reduce that, you get 3/7. Okay, so I feel like we've done a lot of these types of questions on the reviews, on the tests. Let's skip on down a little bit. Okay. Number 6, a committee of 3 people is formed. Committee of 3 people. Okay. The 3 people will be selected from a list of 5 possible committee members. 5 in the pool, basically. Okay. A simple random sample of 3 people is taken without replacement. So that means once I pull Susie Q's name, she can't be on the committee twice, right? So I pull her out. Without replacement from the group of 5 people using the letters A, B, C, D, E to represent the 5 people. List the possible samples of size 3 and use your list to determine the probability that C is included in the sample. Okay, and there's a hint. Okay, so here are my people, A, B, C, D, E, and I want 3 slots, right? So it says, hint, there are 10 possible samples. Okay. Ten possible outcomes or samples. See how this relates back to what we've been talking about all semester in the class. Okay, so let's see what it looks like. What are my choices for the first position? A, I'm just going to kind of try to go straight through. I could get A, B, and C, right? Okay. Now let's just change them out one at a time. So what if I kept the A and the B, but I changed the last guy? It could be a D, or it could be an E, right? Okay. But I can't reuse A or B, and it can't be C because I already got that one. Okay. So now let's start changing something else. What if it was, let's say, keep the A and keep the C? Well, we already did B here, so what other options could there be? There could be a D there, there could be an E there, right? We've already got the B, and the A can't be repeated. Okay, so that's what could happen there. So, what else could happen for the middle guy here? It could be, if I don't keep the C straight here, it could be that the C is in the middle, but then what? There would be a D at the back. And what else? A, C, E. Okay. We could get A, C, B, but what about him? A, C, B, and A, B, C. Did they care about the order for this guy? And the answer is no, they didn't care about order, right? So aren't those the same committee, whether it's Susie, Johnny, and Joey, or Susie, Joey, and Johnny? That's still the same committee, right? So am I going to double count this guy? No. So anything that's overlapping here, I'm going to dump it out, okay? So we're going to have to go back and double check that we've got all of them. Okay, so I think that's probably all of the committees that have A in them, okay? So what if I dump A and I start over, okay? I could have what? I could have the committee that's B, C, D. I could have the committee that's B, C, E, okay? Or I could have the committee that's dump the C, B, D, E. Okay? And I think that any other committees would be that I could list, like A, B, A, E. I already have them, right? B, A, E is the same as A, B, E. B, D, E would, or I'm sorry, BAC would be the same as ABC, so I don't want that one. So I think that's probably it. So that's all the ones with B's in them. And then the last option could be there's no A and there's no B, so how about just the committee that's C, D, and E? Okay. So get rid of any duplicates. And of course, Susie can't serve on the committee twice, so no duplicates there either. And there was a hint that said there's 10 possible outcomes. So I think I've got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, I've got 11, so hang on. 3, 4, 5, 6, 7, 8, 9, 10, 11. So I've got a duplicate somewhere. Let's see if we can find it. Oh, man. A, C, D, AEC. Okay, I've got here AEC and ACE. So that's a duplicate, right? So I'm going to dump that one out. Okay, good. See, we all have to check. Okay, 10 outcomes. That's why sometimes I'll tell you how many to expect. So you have a guideline for where you're going. All right, there's my 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the question was, determine the probability that C is in a sample. Probability that C is in my committee. Okay. Find that probability. Well, that's pretty easy, right? I just come back and I find all the ones that have C's in them. So there's a C, 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 and there's a C. So what do we have? 1, 2, 3, 4, 5, 6, 7 of those. Oh man. Do I have an extra? C, D, E. Man, I hate doing this whenever I didn't work the problem out in advance. I'm sorry. I should have done that. A, B, C, A, C, D, C, E, B, C, E, B, C. C, D, E. So I've got a slight problem because I've got 7 of them. I wish y'all were here. Y'all could tell me what I did wrong. Because sometimes students see it right when you're doing stuff. I've got 7 out of 10, and judging by the answer, it should be 6 out of 10. So let's see what I've got wrong. A, B, A, B, A, B. Let me start over maybe. Maybe I wasn't as organized in my listing as I would have liked to have been. A, B, C, A, B, D, A, B, E. Okay. And then I could dump the B's and I could have A, C, D, A, C, E. And I could have A, D, and E. A, B, C, A, B, D, A, B, E. That's all the options with A and B. A, C, B, A, C, D, A, C, E. So all the options with the A and the C. And A, B, D, A, C, D, A, D, E. So all the options with the A and the D and the E. Okay. So then there's B, C, D. B, D, E, B, D, B, C, D, B, B, C, E, right? And then C, D, E. Okay, there's my 10 options. Let me double check. What did I do wrong? A, C, D. Oh, here's what I did wrong. A, C, D is the same as A, D, E. Excuse me, I should not have had that. That was a duplicate, so that was my problem with my answer. B, C, D, B, D, E, B, C, E, and my problem back here is that I didn't have A, D, E. I didn't have that as one of my options. A, D, E. I was missing that guy. So I had a duplicate and I didn't have this guy in there. Okay, so now I should be good. I'm sorry. See, if y'all were here, y'all would have said, hey, Dr. Webster, ACD is the same as ADC, and we would have found it like that fast and I wouldn't have messed up. But Since you're not here face to face, I have to struggle through on my own, and that stinks. All right, but I think I found the mistake. So here's my list of all my outcomes. There are indeed 10 of them, and now they should all be different. And I've got 1, 2, 3, 4, 5, 6. 6 of the 10 have a C, and the answer that is on the answer key is 3/5. That's why I knew I was in trouble, was because I had 7 out of 10, and that would not reduce down to 3/5, right? Sorry about that. The actual process is not that difficult, right? I think everybody can do that. It's just a matter of making sure you don't do any duplicates, get rid of duplicates, and in my case, I even said that, but then I didn't get rid of all of my duplicates. Okay? All right, number 7. A bag contains 4 chips, of which 1 is red, 1 is blue, 1 is green, 1 is yellow. 1 red, 1 blue, 1 green, and 1 yellow. Whenever possible, I will give you different letters for your colors so that you can abbreviate. Okay. Chip is selected at random from the bag and then replaced into the bag. Replacement. Okay, remember the difference between without replacement and with replacement. If I replace it back in there, that means there's always going to be 4 chips in the bag, right? If I took the yellow and I didn't replace it, so that would be without replacement, then on the second time I drew something out of the bag, there would only be 3 chips in there. Okay, so be aware of that. Okay, then replace in the bag. Second chip is then selected at random. Make a list of the possible outcomes. For example, red-blue represents the outcome that a red chip is followed by a blue chip. And use your list to determine the probability that the 2 chips selected are different colors. Okay, so let's see what we can do here. And it tells me, by the way, there are 16 possible outcomes. All right, so similar thing to what we just did. I can get a red and then a blue. I can get a red and then a green, or I can get a red and a yellow. Does everybody agree? That's with me pulling the red guy first. Okay, if I pull the blue guy first, I can get a blue and then a red, a blue and then a green, and then a blue and then a yellow. Oops, I forgot one. Since we are replacing into the bag, there's one more option for reds. What? A red on the first one, I replace it, and I get a red on the second one. Yeah. And then a blue and a blue. Okay? I can get a green followed by a red, a green followed by a blue, a green followed by a green, and a green followed by a yellow. Okay? Or I can get a yellow followed by a red, a yellow followed by a blue, a yellow followed by a green, and a yellow followed by a yellow. Okay, so real quickly check my sample here. Samples. I have 16 samples that I pulled out of the bag, right? Samples of 2 chips each. That's my sample size, is 2 chips that I'm pulling out of the bag. Okay, so, and remember they said red-blue represents the outcome that red chip is followed by a blue chip. Use your list to determine the probability that the 2 chips selected are different colors. Okay. Okay, 2 chips are, this is what we're after, the probability that 2 chips are different colors. Okay. Well, it might be easier in this case to figure out what's the probability that they're the same. Yellow, yellow, green, green, blue, blue, red, red. That happens 4 times, right? Probability of the same color, and you didn't have to do it this way, but that's the way I see it. This probability that we have the same color is 4 out of 16. Okay. So the probability of different colors would be what? 1 minus 4 out of 16, or 16 sixteenths minus 4 out of 16ths, which is 12 sixteenths. Okay. If you reduce that, that's 1/4. And if you reduce this, this is 3/4. So there's a 3 in 4 chance, 3 out of 4 times, that you will get 2 chips of different colors. All right. All right, so more of that stuff about Probabilities, I don't want to work every single kind of probability. I'm looking for stuff that's different. Let's see. Frequency table below describes the distribution of birds viewed by a bird watching group. Estimate the probability that the group will see a hawk on their next bird watching trip. Okay. So, estimate the probability. This guy is a relative frequency probability. Right? Okay. So, when I estimate this guy, what I want to know is what's the probability, it said for the next bird we see, or the next time we go out, we'll see a hawk. So, they've seen 2 out of how many birds? Relative frequency. The total, right, is what goes on the bottom here. So let's see, that's 14 and 6 is 20, 7, 29. It's 2 out of 29. Does everybody see that? So we've seen a hawk 2 out of 29 times. And whenever I do that math, 2 out of 29, I get 0.06896, and the answer key says 0.069, so they rounded a little bit, but that's okay. So there's about a 6% chance, maybe 7%, we'd probably round that up, right? 6.9% probability of seeing a hawk. Okay, so there's a possibility. It's not a very big possibility. It's only about a 7% chance, but there is a possibility, so it's out there. Okay, so we've got some of that stuff going on. Family with 4 children is randomly selected. Assume the births of boys and girls are equally likely. Construct a table showing the probability distribution for the events. 4 girls, 3 girls, 2 girls, 1 girl, 0 girls. Okay, so I'm just going to say sometimes on these, remember about the tree diagram, right? We did those. So first baby, boy versus girl. Second baby, boy versus girl. Third baby, boy versus girl. For each of these. And last but not least, we've got boy, girl, boy, girl. And remember, we should have a total of 16 paths here, right? Okay, so 2, 4, 6, 8, 10, 12, 14, 16 paths. And we're saying that the probability of each of these happening is a 1/2, right? You've got a 1 in 2 chance of having a boy versus a girl, okay? So there's 16 paths going on here. So one of your questions, even though it's not on the practice test, could be show me a tree diagram for this thing, whatever this thing is, okay? So remember how to do that, and remember how to figure that out. So this guy's probability of, let me pick one down here so I can put it in here. Probability is 1/2 times 1/2 times 1/2 times 1/2. Because we want girl and girl and girl and girl, right? That's a 1 in 16 chance, okay? So that's the first part of this, is just kind of making sure you've got all of your outcomes. If you were just listing outcomes instead of making me a tree diagram, well, they'd be what? Boy, 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 boy. Boy, boy, girl. I'm sorry. Boy, girl. I'm trying to follow my paths. Boy, boy, girl, boy. Boy, boy, girl, girl. Boy, girl. Boy, boy. Boy, girl, boy, girl. Boy, girl. Girl, boy. Boy, girl. Girl, girl. This is so much fun. Girl, boy, boy, boy. Girl, boy, boy, girl, girl, boy, girl, boy, girl, boy, girl, girl. I shouldn't have done the one with 4 children. This is kind of a complicated one. Girl, girl, boy, boy, girl, girl, boy, girl. Girl, 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 boy, and girl, 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 girl. Okay, so there's my 16 outcomes or samples. Okay. And they should match up with my 16 pathways coming off my tree diagram, right? So make sure those are okay there. But that's not what the question on the test review said, the sample questions. Number 12. What it says is, and I'm going to need that to help me out, assume the births of boys and girls are equally likely. That means there's a 50% chance. That's what we did. Okay. Construct a table showing the probability distributions for the events. Okay, so here's my result. 4 girls. That's one event. The next result, 3 girls. The next result, 2 girls. Next result, 1 girl. Next result, 0 girls. Okay, that's what they want to do. And then the probability will be over here. So that's what they mean by a probability distribution. And remember that a lot of times we'll have a total line, right? Okay, well, not here, total, over here. Okay, so a lot of times there's a total. And we want all of these probabilities to add up to a 1 or 100%, right? Okay, now what's the probability that they have 4 girls? We already know this one. There is 1 chance out of 16 that you have all 4 girls, right? Okay. Let me go ahead and do the 0 girls one. I'm going to go ahead and draw my lines here. 0 girls. That would mean what? All boys, right? So that's this guy. There is 1 chance out of 16 that you have all boys or 0 girls. Okay. All right, so think about, remember we said there's some symmetry going on here, so symmetry might help me to get some of my answers here. 3 girls. I've got 1, 2, that's 2 girls, 3, and I think that's going to be, oh, here's 4, 3 girls. I'm seeing 4 times that there's 3 girls. Now, if the symmetry holds out, then there should also be, if I'm correct, okay, that's that, there should also be 4 out of 16 ways to get 1 girl. So let me see. I'm going to circle these in my highlighter. 1 girl, 1 girl, 1 girl, 1 girl. There it is. Okay. So circled. Okay. So that this is 4/16 here and this is 4/16 here. Now, the rest of them should all be 2 girls, guys. 2 girls, correct? Okay. So, and we can do that real fast too, right? There's 5 here and 5 here, so there should be 6 left. But let's check and make sure that first of all there's 6 left, and second of all that they all have 2 girls. So here we go. 1, 2 girls here, 2 girls here, that's 3 of them. 2 girls here, 2 girls here, and 2 girls here. That's 6. Okay, so don't forget about your symmetry in these probability distributions because that might help you as well. It might make life a little bit easier as you work through these things. All right, so that's kind of what a probability distribution looks like, and make sure it adds up to 1, which it does. Okay, so don't forget all that stuff that we've talked about before. Okay, okay, be a little bit careful because there's 2 different laws going on. So, well, there's not laws. So there's the law of large numbers. Okay, and that says that if you repeat an experiment enough times, your empirical probability will eventually approach your theoretical probability. Okay, and that's that law of large numbers. You have to do it a lot of times, right? It's not just I flip the coin once or twice. Maybe it's I flip that coin 2,000 times, right? Okay, so and we have a project that talks about the law of large numbers. Okay, so there's that guy going on, and then on the other side of things, there's the gambler's fallacy. Okay, and remember this one says, a gambler will often believe that he is due for a change of luck, whether it's for the good or the bad. If he's been doing poorly, he might think, oh, it's my turn to win. If he's doing great, he might think, oh, I better quit while I'm ahead. But he thinks he's going to have a change of luck. And the problem with that is, however, the probabilities of winning a game of luck, let's call it a game of chance, doesn't change. That's the fallacy part, right? Okay, so it's not going to change. So he says, oh, I'm due for a turnaround, and that's not true, right? Okay, so just be aware of the difference between those two. All right, what else do we got? Tossing a bunch of coins, game of probability. Let's do an expected value one, and then we might be just about finished with this. So I'm looking on the test review, on the practice problems. I'm looking at number 16, find the expected value. Okay, so it says, in a game you have a 1 in 26 probability of winning $123 and a 25 in 26 probability of losing $7. What is your expected value? Okay, so remember that expected value is always the probability of event 1 times the value for you of event 1. And you just keep on going. The probability of event 2 times the value for event 2, and so on and so forth, right? And depends on how many different possible outcomes there were that you were looking at, right? So for this one, there's only 2 probabilities given. One was you have a 1 in 26 chance of winning $123. Now, if I'm the one who's playing this lottery game or whatever it is, then that's a positive for me, right? Positive $123. Okay. But there's also, if there's a 1 in 26 chance of me winning, then there's a what? 25 out of 26 chance of me losing. And apparently the lottery ticket or whatever, they're saying it costs $7. Okay? That value is $7 or loss. Okay? Now, what is that looking like from my end point whenever I have to give them $7 for the pleasure of playing? That's a negative, right? It means for sure I am shelling out that $7. I can't win if I don't play, so I better pay my $7 if I think I'm going to be lucky, right? All right. So, what does that mean? Well, let's do some math. 1 in 26 chance of winning, 1 out of 26 times 123. Okay, so that's a positive 4.73. Okay, plus, let's see what this looks like. 25 out of 26, that's really close to 1, right? Okay, so it's 0.96 times 7, but it's negative. Let me go ahead and throw in the negative 7 just so we can see it in there. Okay, that's a negative 6.73. Okay, now Positive and a negative means subtract, right? So 473 positive and a loss minus, excuse me, 673 means what? It's a negative $2. Okay, so hopefully you can see that's a negative $2 I'm losing for sure. Okay, so my expected value at playing this game of chance that they've got listed for me on number 16 here is it's expected that I'm going to lose, and I'm going to lose $2, right? Now that doesn't mean that the 1 in 26 person doesn't win $123. Congratulations to that person. But the fact is they can't run a lottery or a raffle or whatever these things are if they don't have enough people buying so that they say, yeah, 1 in 26 wins, but we get to keep that $7 from 25 of those people, right? So they got to make sure it averages out so that even though this one guy gets this money, these others are not. Okay. All right, there's a couple of kind of terminology things in here, so I want to make sure you remember these. Number 20 says, determine whether the event is independent or dependent. So remember, independent means that whatever happens between them, the probability of one is completely separate from the probability of the other. But dependent means that the probability of one will affect the probability or change the probability for the second event. Okay, 2 successive jacks are drawn without replacement. Okay, what that means is I pull a jack out of the deck of cards, I don't put it back in. Okay, so what does that tell me about the number of cards in the deck? It was 52. I pulled one out. Now it's only 51 because I'm not putting it back in. Okay, so what do we know about whenever I go to pull that second jack? The probability is going to be 3 of them. There's only 3 jacks left out of 51, right? So it changes that probability for the second draw. Okay, that means that the second probability is dependent on the first probability. Okay, so if they don't replace, then those are dependent events. Okay, red ball is drawn from a bag containing 4 red balls and 2 black balls. It is replaced, and then a black ball is drawn. What about that? It is replaced. Did we change the probability? No, because we put that ball back in, right? Okay, so lots of probability for this exam. Make sure you know the probability of something for sure happening and the probability of that something will not happen. So let's just remind ourselves the probability that we'll roll a 10. Oops, let me start over. Sorry. The probability that we'll roll a 10 on a 6-sided fair die. Sorry, that's kind of long. What do we know about a 6-sided fair die? It has sides 1, 2, 3, 4, and 5, and 6, right? So what's the probability that I'm going to get a 10? There's 0 out of 6 possible, right? So what's that? That's a 0, or a 0% probability, okay? But what about if I said the probability that I'll get a roll less than or equal to 6? Again, on this same 6-sided fair die. I just don't want to write it again. Probability that when I roll, I'll get something less than or equal to 6. Well, all of the dice, all of the sides on this die are less than or equal to 6, right? So that's a 6. The 1 is less, the 2 is less, the 3 is less, the 4 is less, the 5 is less, the 6 is less. Out of 6 possibility, so 6 out of 6 is a 1. There's 100% chance that I'm going to get a 6 or less on that same 6-sided die, right? Okay, so make sure you know if the thing that I'm asking you about is absolutely impossible, there's a 0% chance, right? So the probability is going to be 0. But if it's guaranteed to happen, like this one, it must be a 6 or less, then the probability of that one is 1. Okay, always going to happen. So never versus all. So make sure you know the difference in those. Work through the rest of the problems. I'm not going to work them all because it's already getting to be a long video here, so just go through and play with some of those. The answers are on the back, like I said, and if you have any questions, let me know. Good luck studying and have a great day. Talk to you later.